A warm welcome. This is Control Systems course, lecture 3.1, focusing on frequency response. Frequency response. Normally, we have seen about the time response, where the response varies with respect to time. And in case of frequency response, the response or the output of the system will be varying or considered with respect to frequency. Normally, almost all the systems can be represented in frequency domain. Actually, the frequency domain way of evaluating a system is very much advantageous when compared to the time response analysis. The response of a system for a sinusoidal signal is called sinusoidal response. The ratio of sinusoidal response to sinusoidal input is called sinusoidal transfer function of any system. And in general, that sinusoidal term will be considered as a j omega instead of the Laplace transform s value. The s value can be simply replaced by j omega, where omega is the frequency value. It is the angular frequency which is being considered. So the frequency way of analysis is very much important and informative when compared to the time response. So what type of analysis can be considered in frequency responses? We can consider two main functions in the frequency response analysis. One is the magnitude function, the other is the phase function. So we can consider the magnitude value of a term as well as the angular term. For example, instead of the Laplace transform parameter s, we are going to consider j omega. J itself is an imaginary term. So now we are making the system into a complex function of the omega. So when complex function is entering into the field, we can analyze the system in terms of magnitude as well as phase. So we have numerous types of plots which can be used for frequency response analysis. Before that, let me introduce the open loop transfer function, loop transfer function, as well as the closed loop transfer function of the system. Open loop transfer function, g of j omega, which can be represented by its magnitude as well as phase or angle value. Loop transfer function is nothing but g of j omega into h of j omega. And closed loop transfer function, if suppose it is a negative feedback, then it can be represented as m of j omega is equal to g of j omega divided by 1 plus g of j omega into h of j omega. So this is what is the representation here. Let us come across with the frequency domain specifications. Already we have seen about time domain specifications in time response analysis. Similarly, frequency domain specifications are the values which can represent the frequency analysis, how the analysis is going on, whether it is right or wrong, whether the value has to be increased or not. We can analyze the frequency response through these domain specifications. Let us start first with the resonant peak. So the resonant peak is a value where the maximum value of the magnitude of the transfer function can be obtained. A large resonant peak will correspond to large overshoot in transient response normally. So let us consider the closed loop transfer function here, where the second order system is being considered. So already we have seen this equation. It's the standard form of second order equation. This is the transfer function, omega n square divided by s square plus 2 zeta omega ns plus omega n square. Let us substitute s is equal to j omega. On substituting, we'll have the imaginary term introduction. And then what we are doing is, we are just substituting the value for j omega. Since it is a square term, it becomes minus omega square. Rest others are same. And let us take omega n square outside, because in the numerator part we have an omega n square. So let us cancel out this. For that purpose, we are taking omega n square commonly outside. Since we have only minus omega square here, it becomes minus omega square by omega n square. Here we have already a omega n term, and so we have plus 2j zeta omega divided by omega n, plus this omega n square can be taken outside, so it becomes 1. So this omega n square and omega n square get cancelled, and this becomes 1 divided by 1 minus omega square divided by omega, omega by omega n the whole square plus 2j theta omega by omega. We know what is u formula. U is equal to omega by omega n. So ur will be equal to omega r divided by omega. That will be, so taking ur is equal to omega r by omega n and equating the value of ur, we get omega r is equal to omega n into square root of 1 minus 2 theta square. This is resonant frequency value. Next one is the bandwidth. So what is the bandwidth? Bandwidth is nothing but range of frequencies. Why we are providing range of frequencies? Actually, we can allow a signal to pass through, with certain frequencies, certain frequency or a single frequency, either the term. If it is allowed through a range of frequency, then the frequency should have, the bandwidth will have an upper limit of frequency as well as the lower limit of frequency. The difference between the upper limit and the lower limit will give you the range of frequency through which the system can have its normalized gain value to be minus 3 decibels. In frequency domain analysis, the bandwidth is the range of frequency where the system's normalized gain value is more than minus 3 decibel, and the frequency at which the gain is minus 3 decibel is called the cutoff frequency. This is a most important point. So let us consider the bandwidth condition also. Let us represent it by omega b. The normalized bandwidth is considered to be ub, which is equal to omega b divided by omega n. And here when u is equal to ub, that is during the bandwidth time, the magnitude of the closed loop system is said to be equal or greater than minus 3 decibel. So we are taking this minus 3 decibel as 1 by root 2. This is the equivalent value. This is in decibels value. This is a magnitude value. So it is 1 by root 2. So let us equate m value, the magnitude value of m, to be equal to 1 by root 2. Upon equating this and then substituting, because here we have power 4, so we have taken x is equal to ub square, then x square term, it's a quadratic term. So on applying the formula of x is equal to minus b plus or minus root of 4 b square, b square minus 4ac divided by 2a, we have this set of calculations, and we've come across with the x value here. So in substituting x as ub is equal to root x, because x is assumed to be ub square. So ub is equal to square root of x. So now we have ub is equal to the square root value. Already we know ub is equal to omega b divided by omega n. So omega b is equal to omega n into the value. This is what is called the bandwidth for the frequency domain. And next is the cutoff rate. Cutoff rate is nothing but the slope of the log magnitude curve. We have already seen that we have a magnitude and the phase angle. So here this magnitude curve will be represented in the logarithmic scale. That's why we are considering it in decibels terms. So the slope of the log magnitude curve near the cutoff frequency is called the cutoff rate. The cutoff rate indicates the ability of the system to suppress the signal or separate the signal from the noise. This is what is called cutoff rate. And the next frequency domain specification is gain margin. This is the most important one. We have gain margin as well as phase margin. So margin is the value, that's the edge value. It represents an edge value. After that, the system will become unstable. This is what is the condition. So the gain margin is defined as the value of the gain which is to be added to the system in order to bring the system to the verge of instability. After that, the system will become unstable. So that's the crossing value or the edge value. The gain margin is given by the reciprocal of the magnitude of the open loop transfer function at phase crossover frequency. So what is phase crossover frequency is that the angle should be 180 degrees. The angle should be 180 degrees. What is the frequency of the phase of the open loop transfer function at 180 degrees? This is what is called phase crossover frequency. Normally, if we consider, let us have we'll have magnitude values and we have phase values. Phase values in the sense it is from 0 degrees to 360 degrees. That's what the phase value. So at that phase values, 180 degree is a part. It's a well-known factor. So at that 180 degree, we have to find out what is the frequency at which the phase of the open loop transfer function becomes 180 degree. That frequency is known as phase crossover frequency, and only at that phase crossover frequency we can find out the gain margin value. None other frequency will be representing the gain margin. So since already stated, one is kg is equal to 1 by modulus of g of j omega pc. So representing this in decibels, we have 20 log of kg. This is what is the gain margin value. It will be indicating the additional gain which can be added to a system without affecting the stability of the system. After that, it will be unstable. This is what is the condition. Normally, the gain margin of a second order system is infinite. Now coming to phase margin, the phase margin is represented as gamma and is defined as the additional phase lag which is to be added to the added at the gain crossover frequency in order to bring the system to the verge of instability. So now what is gain crossover frequency? So it is the frequency at which the magnitude of the open loop transfer function is unity. There we have seen that the phase of the open loop transfer function is 180 degree for phase crossover frequency. In case of gain crossover frequency, it is the frequency at which the magnitude of the open loop transfer function is unity, or the magnitude in decibels. That is the general magnitude. If it is represented in decibels, then that decibel magnitude should be 0. Whatever the condition you consider, it will be the best. Now let us have a small derivation for this phase margin value. Let us consider the open loop transfer function. G of s is equal to omega n square divided by s into s plus 2 zeta omega n. Substituting s is equal to j omega, we'll have this equation, and from this what we are going to do is we are going to take omega n square outside. So let us take omega n square, and then let us cancel out the numerator and the denominator omega n squares, and after that see the equation. Here we have omega by omega n, which is nothing but the normalized frequency u. So g of j omega is equal to 1 by ju into 1 ju plus 2. Already we have found out the phase value. It is minus 90 degree minus tan inverse of u by 2c. Let us substitute it here. Minus 90 degree minus tan inverse of, instead of u, we will have UGC by 2 zeta. Already we have the UGC value. This when gets substituted here, we'll get the equation reduced to this form. Gamma is equal to 90 degree minus tan inverse of minus 2 zeta square plus root of 4 zeta power 4 plus 1 the whole power 1 by 2, or the square root simply divided by 2 zeta. This is how we have to find out the phase margin. And this is a typical magnification curve of a feedback control system. This is the omega p value, which is nothing but the resonant frequency, omega p, and here we'll have the resonant peak value mp, and this is the range of frequency. So this will be our bandwidth at 1 by root 2 value. That's all. Thank you.